All right, so in this section, we're really just trying to look at some of the major ideas that drove the discovery of limits in calculus. And so we're just looking at a couple different applications of where we can use these ideas to find some practical results. So we found this equation of a tangent line, which we'll see has lots of applications later on. And what we want to do now is look at an application in physics to start generating, again, this technique for finding limits that we're learning about. So some basic notation that we need to make sure we understand before we start the problem. First of all, S of t refers to the position. So S is a common notation for the position of an object or particle in physics. Of course, this little triangle here, that's delta. Delta is a letter that we use to denote change, like we've seen in the slope formula, delta y, delta x. So delta S then would be the change in position. In other words, your final position minus your initial position. Really, those should be reversed. Probably that should be T2 over minus T1. So it kind of doesn't make too much of a difference, but final position minus initial position, that's called displacement. How far are you away from where you started? Okay, you're familiar with the idea of velocity. Velocity is the rate of change of position. That is both a magnitude and direction, so positive 30 miles per hour or whatever, but you can have negative velocity as well. But that's just the rate of change of position. So that would mean that average velocity can be found by taking your change in position divided by your change in time, right? Change in position divided by change in time. In other words, S sub t2 minus S t sub 1, over t sub 2 minus t sub 1. Okay, this would be our average velocity function. You'll notice it looks very much like the slope function or slope equation. So that's how we find average velocity. All right, if a car is driving from one place to another, its velocity goes up and down, and what you would do is take how far did you travel divided by how long of a time did you travel, and that would tell you your average velocity. But you know it's changing from moment to moment within the trip. So our next question is then, how would you find instantaneous, not minus the ly here, how would you find instantaneous velocity, right? How can we know velocity at a particular instant? And that's what we're interested in right now. We're going to do a problem here. It's going to look very similar to the last one we did, where we try to figure out instantaneous velocity. So let's read the problem. It says a stone is released from a state of rest and falls, that should have a S there, falls to the earth. Its position in meters at time t is given by the function S of t equals 4.9 t squared. Okay, and this is one of Galileo's formulas that you'll learn all about in physics. But let's estimate the instantaneous velocity at t equals 8. So again, the idea is we do know what average velocity is. Average velocity is S sub of t sub 2 minus S of t sub 1 divided by t sub 2 minus t sub 1. Right? In this case, we know that position is given by 4.9 times t squared. So we would do 4.9 times t2 squared minus 4.9 times t1 squared. Right, all over t2 minus t1. Okay, we want to know what the instantaneous velocity is at point 8. And so here's the idea. We can't find average rate of change with a single time. So what we're going to do is say, well, at 0.8 seconds, his instantaneous velocity was probably very close to whatever his average velocity was over the following tenth of a second, say. Okay, and so what we can do is find average velocity for from 0.8 seconds to 0.9 seconds. Okay. Okay, and that would be equal to the position at 0.9 seconds minus the position at 0.8 seconds all over 0.9 seconds minus 0.8 seconds. Okay, in other words, 4.9 times 0.9 squared minus 4.9 times 0.8 squared divided by 0.9 minus 0.8. And so obviously this is going to be pretty calculator intensive, and I'll show you how to use Excel to like make this go a little faster, or you can use a graphing calculator, of course. But really the form of this is more important right now. I know you know how to type things into a calculator, so I'll just simplify this down for you here, and you would get 8.33 is what you're going to get for the average velocity from 0.8 to 0.9. Now this is an object that's falling in meters. It doesn't say so, but this is, it does indicate here seconds, so this is actually going to be meters per second. That's its velocity. It's falling at 8 meters per second, 8.33 meters per second. And so the idea is this is an approximation. At 0.8, it would have been somewhere close to that, but probably not exactly equal to that. So what we want to do now is take this interval from 0.8 to 0.9 and shrink it down and look at all the different intervals that contain 0.89 or 0.8 as an endpoint. So what we want to do is think about these intervals. So we could say, let's take the interval from 0.8 to 0.9. We did, or excuse me, 0.9. We did that one. But then we saw that the average velocity was 8.33. But then let's shrink it down. That was 1/10 of a second. What would it be if I took only a 1/100th of a second? And then what would it be if I took only 1,000th of a second? Right, from 0.8 to 0.801. And then what would be if I took only the 10,000th of a second immediately after the moment that I'm concerned with? Obviously, we could agree that a 1/10,000th of a second is so short of a period of time that is pretty close to what we would call an instant. Now, an instant means no time passes, though, so we have to keep getting that interval shorter and shorter and shorter, and take the average velocity over increasingly small intervals of time. That average velocity is going to get closer and closer to the instantaneous velocity. As this interval gets closer and closer to 0 seconds, the average velocity gets closer and closer to the instantaneous velocity. So let me fill in these values for you. Over this 1/10 of a second interval, we'll see that the average velocity is 7.889. In the 1/10 of a second immediately following the instant that we're concerned with, they were traveling at 7.889 meters per second on average. If we shrink that interval down to 1,000th of a second, they were traveling on average at 7.8449 meters per second. If we shrink it down to a 10,000th, we'll see they were traveling at 7.8405 meters per second. If we did go just one more unit or one more interval shorter, 1/100,000th of a second, we'll see that the average velocity was 7.84005. And so now we can see a pretty clear pattern that as this interval becomes infinitely short, and in other words, it gets closer and closer to being an instant in time, the average velocity gets closer and closer to 7.84 meters per second. Again, as the interval gets infinitely short, or infinitesimally long, however you want to phrase that, gets very, very short, closer and closer to an instant. An instant is a moment in time with 0 length. The average velocity gets closer to 7.84. We can see it's getting closer. Oops, sorry. We can see it's getting closer and closer to 7.84 meters per second. So we say it gets closer to 7.84 meters per second. Okay? And this is the key idea. Since the average velocity gets closer and closer to 7.84 meters per second, we're going to go ahead and make the intellectual jump and say, then if infinitely short intervals lead to an average velocity approaching 7.84, we're going to go ahead and say that the instantaneous velocity at t equals 0.8 exactly is 7.84 meters per second. That's a big jump. Okay, what we're saying is as the interval gets very, very short, the average velocity is very, very close to 7.84. It's a big jump to say that at exactly 0.8, the instantaneous velocity is 7.84, but it feels very comfortable when you look at these tables. The evidence is overwhelming that it's going to be getting closer and closer to 7.84, but that still is a big jump, and we won't get into in this chapter or even next year in the fall the very thorough way of proving this, but it is a well-established, well-proven concept, this idea of limits. But that's what we can say is the instantaneous velocity at 0.84 seconds after the stone was thrown will be 7.84 meters per second.